Trends in the alkali metals. I'm just going to talk about these real fast. As we go down in the column, we've got increasing atomic radius. The density of these increases and their reactivity increases. The things that decrease as you go down are ionization energy, electron affinity, and melting point. In general, alkali metals have very low ionization energies. They will lose an electron quite readily. They're easy to oxidize. They're very reactive. You don't find pockets of elemental lithium or sodium in nature. They're very reactive. They react rather explosively with water, and water's all over the place. So you can imagine you're not going to find any sodium sitting around. And their compounds are generally very soluble in water. They react vigorously with nonmetals. So here we're using M as saying, well, this is a generic alkali metal. Could be lithium, potassium, whatever. Going to react with a halogen, could be chlorine, fluorine, etc., and they're going to form an ionic compound. They react explosively with water, and you end up with the metal hydroxide in solution and hydrogen gas being given off. So here's an example of lithium in water. It's reacting. Here's sodium in water. It's giving off hydrogen gas and enough heat that the hydrogen ignites. Potassium is more reactive, and so this is fizzing, and basically it's a small explosion. If you had a bigger piece, it would be a big explosion. And so you can actually look up YouTube videos of idiots throwing chunks of sodium into their swimming pools and stuff. Not a good idea. The good thing is you have to get the sodium first.
Why is that a bad idea?
Because it reacts explosively with water.
No, there's a science teacher at my high school who did that into our swimming pool. He had a chunk of sodium in the swimming pool, and it was great.
Yeah, but it's potentially disastrous. If you do it in a lab, throwing it in a sink, you can just explode the end of the bench off. People can get hurt. So there's a reason that you can't buy sodium at Walmart, right? Trends in the halogens. We see trends in density, melting point, etc. Halogens have very high electron affinities, large negative electron affinities. They are good oxidizing agents because an oxidizing agent becomes reduced. Reduction is gain of electrons. So they gain electrons easily, causing other things to be oxidized. They are also very reactive. And their compounds are also generally soluble in water. So the halogens react with metals to form metal halides. How many of the halide ion are with the metal depends on what the charge on the metal is. And they react with hydrogen to form hydrogen halides. This is an example of a reaction. I think that's sodium with chlorine. It makes sodium chloride, but it gives off a lot of energy. Okay, so this sort of a question I would think is going to be pretty challenging for most Chem 1A students, but we're going to give it a shot anyway. Write balanced chemical equations. So the reaction between aluminum metal and chlorine gas. And the way you would do these is not by just memorizing, but maybe using a little bit of common sense. So we've got aluminum and chlorine gas. What's the formula for elemental chlorine? Cl2, because it's one of the 7 diatomic ones. So chlorine gas and those react. Well, you've got a metal and a nonmetal. What are they probably going to do? Make an ionic compound? What charge does an aluminum ion have? 3+. What charge does a chlorine ion have? -1. So they're going to make their regular ions, and then they're going to combine in a way that they end up being neutral, right? So we're going to get Al Cl3. And then we would have to balance it. This is a solid, that's a gas. If these were aqueous, then this might be aqueous, but apparently there's no water around. So is an ionic compound a solid, a liquid, or a gas at room temperature? It's a solid. Ionic compounds, those ionic bonds are very, very strong and they have high melting points. Ionic compounds are solids at room temperature. And then we would need to balance it. So we'll do 3 here and 2 there and a 2 over there. Any questions? Lithium metal and liquid water. So lithium metal and water. What do we do? So what happens, what makes these reactions with water so explosive is that it generates hydrogen gas. Hydrogen gas is flammable, and there's enough energy there that the hydrogen will spontaneously ignite. So hydrogen is going to be one of the products. So we're going to get hydrogen gas. And then we've got lithium, and we've got part of the water, right? So we're going to have lithium makes a +1 ion. If we take an H away from the water, we're going to have hydroxide ion. And so it's going to make lithium hydroxide. Since this is in liquid water, that would be aqueous. And then balancing this, and 2 of these, and 2 of those, and 2 of those. I would not expect you to get that one right, necessarily. That was the toughest one of these. Let's look at this one. Gaseous hydrogen and liquid bromine. So hydrogen is a diatomic element, and that's a gas. And liquid bromine, diatomic element. Well, we got to put them together somehow. This is going to make HBr, which, if it's dissolved in water, would be hydrobromic acid, H plus and Br minus. So that's going to make HBr. That's going to be a gas, but I wouldn't expect you to know that. So if you're faced with a situation where you have to predict products for something like this, think of the ions and how those might go together. And this slide is not a big deal. Trends in noble gases. Oh, these trends are boring. Going down, these things change. They are exceptionally unreactive. Unlike the other 2 groups that we looked at, these are only found uncombined in nature. There were no noble gas compounds known before the 1960s. Yeah.